laser that happened to laze right at the silicon band gap, right? Because then we wouldn't have this problem where the photons are just spread all over creation, and a lot of them are too low in energy to be absorbed. I put silicon, but you can insert your favorite organic to this diagram, put your band gap wherever you want. So you waste a lot of low energy photons that just pass through and don't do anything. Now the high energy photons will get absorbed. They're above the band gap, but they quickly relax to the band gap edge. So you came in with, say, 2 eV of energy, but one of those EVs just becomes heat, right? The other EV can be used to drive electron hole separation and become a voltage. Okay, so you waste a lot of photon energy in solar cells. That's what limits a single junction solar cell. The theoretical limitation is 33, 32%, depending on how you do your calculation. A big part of that limit is just the fact that you have to work with the sun. Again, if the sun were a laser, if you could concentrate everything at this band gap, you would have a much higher efficiency solar cell. So one question is how much higher? And we'll talk about that. I'm going to be doing some walking here. So people recognize this for a long, long time. And the strategy is just take the sun and make it what you want to be. Convert those photons one way or another. If you have 2 low energy photons that are below the band gap, they're going to pass through the band gap. Don't let them do that. Put in some material that will up-convert the photons to a single high energy photon. You can absorb that photon and generate your carrier. Alternatively, if you have a high energy photon, turn it into 2 low energy photons. The energies have to be above the band gap, but then you can get 2 carriers, not just one thermalized hot carrier, but 2 carriers for the price of that single high energy photon. This is all photon to photon conversion. There's a big market in that, including in Australia. Some of the founding members of this, they call it quantum cutting. That seems to be the new, you put in quantum, I guess, when you want it to sound better. Mainly based on lanthanide glasses, okay? So there are a lot of big drawbacks to the approach that people are taking for these photon-to-photon conversions. The other way to do it is just do your conversion in the material that you made your solar cell out of. And this would be exciton creation. And so there are 2 general phenomena there that I'm going to talk about. In all cases, it's going to be this down conversion. The analog of that is what you do in a device, okay? So up here, even if you make those 2 photons, you still have to absorb them. Here, you absorb the photon, and then you make 2 excitons. Okay, so in principle, you should be higher efficiency because you don't have to worry about optical coupling and things like that. So a lot of attention recently in inorganic nanocrystals for what's called multiple exciton generation. Technically, everything that I'm going to talk about falls under the rubric of multiple exciton generation, but to clarify multiple exciton generation, I'm only going to refer to the inorganic systems where you absorb a photon, it creates an exciton, a high energy exciton that quickly splits into 2 or more lower energy excitons of the same spin multiplicity. Okay, so singlet to singlets, for example, if you can really classify Wannier excitons in inorganics that way. In organics, the more common process is what's called exciton fission, which is where you absorb that high energy photon, create the high energy singlet, and it splits into 2 lower energy triplets. Okay, that's a spin allowed process, right? Singlet to triplet is spin disallowed. You need some funny thing to make that happen. You have to flip a spin. But as we'll see on the next slide, you don't need to flip a spin to create 2 triplets from a singlet. And then you have to figure out some way to ionize those triplets, and then you're in business, right? Then you can get that efficiency gain. So before I go too far, let's talk about what are those efficiency gains. What's the maximum that you can get out of this type of approach? So a single junction cell is going to be 32, 33%. Down conversion exciton fission, it turns out the calculation is the same. Whether you do it in photons or excitons, you're going to get the same efficiency gain. And the maximum you're going to get is about 42 or 43%, depending on sort of some details in the calculation. So you can go from 32% to 43%. Turns out up conversion, where you get the low energy photons and just make them into high energy photons, is even better. You can get up to 46 or 47%. If you combine them, you hit the 50% mark, 49, 50% total efficiency for a single junction cell. This is all theoretical. But the point here is that these gains, these proportional gains, this 33% gain, should be applicable to any solar cell. So if you want to use amorphous silicon or something like that, if you can more efficiently harvest the photons, you should get that 30% gain in efficiency. So 10% to 13% or 30% to 40%. That type of gain should be general, no matter what your base efficiency is. Okay? You don't need the perfect silicon cell to have this work. So it should be a general strategy to raise solar cell efficiencies, okay, no matter what the solar cell. We like exciton fission for this approach, and these are some of the reasons that I like exciton fission. One is that it's organic, and I like organic molecules. That's my prejudice, so that doesn't count. The main thing here is, one, if you make triplet excitons, okay, where the spins are, you have two spin states, usually they're spin up, spin down, but in a triplet, just, this is for the physicists in the audience, and just a quick review. For a triplet, it's spin up, right? So they're unpaired, it's a higher energy state. But they are very long-lived. Your singlet exciton is going to live for maybe 5, 20 nanoseconds. Okay, so if you're going to ionize it, you have to do it within that lifetime. Triplets are much longer lived, typically microseconds or even milliseconds in crystalline anthracene. So you have orders of magnitude longer times to ionize those triplets. Now they're going to be harder to ionize typically, but you have all kinds of time to figure out how to do that, and all kinds of time to diffuse around the device. Okay? Even though triplets are typically slower in diffusing than singlet excitons, if you have 1,000 times more lifetime, you can still go much farther than you could, even if you're hopping quickly. If you hop slowly, but you have 1,000 times longer to do that, you're going to go farther, right? So the exciton harvesting problem becomes easier with triplets. Also, it's a bulk phenomenon in these organics, and I'll show you a huge long list of organics where it's a bulk phenomenon. You don't need to quantum confine your excitons into a nanocrystal, right? The big problem, or one of the big problems with multiple exciton generation, you've got those two excitons, you make them a very high efficiency, up to 7 even, but they're all trapped within some tiny ball, and very quickly they recombine, and you lose those excitons. So the time scale that you have to harvest excitons in a nanocrystal is the time scale that it takes them to recombine, and that can be 10 picoseconds or 100 picoseconds in, say, lead selenide. So you don't have to worry about that. Here you have all kinds of freedom to diffuse away in the bulk. You don't have the same kind of recombination problems that you have for nanocrystals. Last point is there are materials where it's, again, we'll debate this a little bit more later in the talk, where it's a very well-established phenomenon. They've already been made into solar cells, right? They're already components of functioning OPVs, not very efficient OPVs, not comparable to the polymer bulk heterojunctions, but these materials that exhibit exciton fission can be and have been incorporated into actual devices. Yang, Kipling, and Carl Nito also have done this, so some respectable people. Let me talk a little bit more detail about what is exciton fission. Okay, so let's talk about the dynamics. You've got molecule A and molecule B, right? We need at least 2 molecules if we're going to fission, because we need 2 sites to have those 2 triplets on. So we need 2 molecules, so that's a 4-electron system. Each one has 2 electrons. Start out in the ground state, spin up, spin down, spin up, spin down, 2 singlet ground states. Put in a photon. Now I have a singlet excited state, right? Spin up, spin down, but now one's in the higher Lyman orbital. The key step for exciton fission is this intermediate step where you transfer this electron over to its neighbor. No spins have flipped, but now you've transferred an electron. You could transfer an electron back. Logically, you think it would be this one, but it turns out that this is the electron that goes over back to A. So you end up with up, up, that's a triplet, down, down, that's a triplet. Now you have your triplet pair state. The key point here is the intermediate is this charge transfer state. Now, whether that's a true intermediate state or just a virtual state that doesn't have any real population when the process occurs is a matter of debate. Nobody really knows. You could imagine a concerted 2-electron process where this just, you go from here to here without this intermediate state. And I think there's a lot of strong evidence that that's actually the case in Tetracene at least, but I won't get into that debate. What are the materials where you can have exciton fission? There's a whole zoo, and there's more coming all the time. So we'll talk about that in a little bit. First observed in anthracene, or used to explain fluorescence dynamics in anthracene back in 1965. Parylene, AlQ3, polydicetylene, recently P3HT. There's a claim that exciton fission plays a role in P3HT. I wouldn't say that's a super strong claim, but it is a claim. It's published in JACS, so that's good. Pentacene, again, there's some debate here. We'll talk about that. Carotenoids, that's a classic system for exciton fission. Very old. The role of the sort of bound triplet pair state versus separated triplets. Mike Tober has some very interesting results recently. They may be published by now, I'm not sure. On carotenoids. Diphenylisobenzoffuran. This is the favorite of Joseph Mickel and his army over there, Mark Gretner and Art Nozick. And there's been a lot of stuff published on this molecule just recently. Carbon nanotubes, very exciting results by Paul McEwen's group, where he measures electron hole pair generation in a totally different way. Multiple exciton generation, maybe. And then tetracene, which is my favorite. And this is a partial list. Okay, there's lots of other molecules where this has been observed. So it's not like this is a flash in the pan type of thing, right? It's a known, relaxation mechanism in condensed organic phases, okay? And it's been observed in many molecules, and it'll be observed in many more. I can guarantee you that. So what we got interested in is, if you notice that previous list, all of those observations were in aggregated systems, or molecular crystals. Okay? Nobody had seen it in just a single molecule, and we set out with Cosmolan to make Tetracene dimers. Tetracene is a nice molecule because its triplet energy is almost exactly half of the singlet, right? You have to conserve energy. And we just made these dimers and said, can we make these dimers undergo exciton fission? Absorb a photon, create an excited state on one part, and then have it split into two excited states, two triplet states separated across this molecule. And then you can imagine, you go with the Reckner-Mickle picture of absorbing this on a TiO2 surface, fission, then you've got these two excitons. You can easily do charge injection from triplet excitons into TiO2. People do this in the dye-sensitized cells all the time. So you imagine putting maybe some carboxylic acids on this, absorbing it to TiO2, and making a higher efficiency Retzel cell. That's the idea that was in that JAX paper by Ratner and co-workers a few years ago. So we can make these. I'll talk about the nature of the molecules. You always have to worry about, these are molecules. So one question is, I draw them as all being flat, but that's not what they're like. So it turns out they're quite floppy. Because of the hydrogen-hydrogen interference on the central phenyl ring and the tetracenes, that phenyl ring does not lie flat. It flips about 90 degrees relative to the tetracenes. What that means is you don't get good pi conjugation across the whole molecule, right? If you looked at my drawing before, you'd say, oh, maybe you could get an electronic state that's nicely delocalized over those pi orbitals. That's not what you're going to get in these systems because the linker flips out of registration with the tetracenes. And what's more, these are very floppy molecules, okay? In solution, they're not rigidly held that way. The barrier to rotation is less than a kT. So basically, you've got a couple of tetracenes flopping around in solution. And you know that's probably true because you can look at the absorption spectrum, right? We had very strong electronic coupling between those two tetracenes. Here's the absorption spectrum of tetracene. We spend a lot of time in our group just staring at absorption spectra, trying to figure out what they mean. Not super exciting science maybe, but it keeps you from making big mistakes, I would say. Here's the linkers, and to the untrained eye, they all look identical, right? Just everything looks the same. It looks like you have two independent tetracenes. There's some changes in oscillator strength. There's some slight changes, redshifts, some slight changes in the vibronic line shape. But to first order, they just look like independent tetracenes. So we're really dealing with monomeric tetracene here. We don't see any subatomic shift. In other words, there's no charge transfer states nearby to affect this because when we put it in different polarity solvents, we don't see anything change. Right? So there's not any involvement of charge transfer states. They're probably way too high in this molecule to have any effect. So the next question is, these are molecules, how do we detect it? Tetracene has this nice feature that I was mentioning before. The singlet and the two triplets are comparable in energy, so you can actually go back and forth between them. So you can absorb a photon, create a singlet state, split into your two triplets. So you can see some fluorescence here. The two triplets are dark. They'll go along for a while, but it's thermally allowed for them to recombine later and recreate the singlet at some time later. That's called delayed fluorescence. And it's delayed by the delay of a lifetime of the triplets, basically. So instead of seeing a nice straight line exponential decay, you see a decay, and then you see a second component that can last for quite a while. That quite a while is the triplet lifetime, the triplet pair lifetime in your molecule. And this is the only mechanism you can get to get this delayed fluorescence phenomenon in these types of molecules or in the solid. So this is a nice sensitive way to detect exciton fission, to detect the presence of triplet pairs. You just have to detect the singlet fluorescence, right? So you can look at very low yields, which is what we needed in this experiment. So when you do these, look at the dimers. Tetracene, to make sure it's triplets, we add oxygen, right? Oxygen is a very nice triplet quencher. So you can sort of put oxygen in, take oxygen out, and that tells you, okay, this is not some other artifact or some baseline problem or something like that. With tetracene, no effect at all, right? There can't be exciton fission. There can't be triplet pairs of tetracene. It's just a molecule by itself. But with these bis tetracenes, at least with the para-linked, para-biphenyl, and paraphenyl, with and without oxygen, you clearly see a long delayed fluorescence component, almost a microsecond for the single phenyl, much shorter for the biphenyl. I don't think I'll be able to get into those details. Again, nothing detectable really for the meta-linked phenyl group. Okay, so 2 out of our 3 worked. You see this delayed fluorescence component. It says that this triplet pair is lasting for about a microsecond. You create it, it sort of sits around, and then it recombines and generates fluorescence. So We get it. We know it's delayed fluorescence. Here's just a control experiment showing that the spectrum at a microsecond is the same as the spectrum at a nanosecond. Okay, it's all coming from the singlet state. It's not like we have some impurity or some other state that's confusing us in the time decay. Right? So this is just a control experiment to say that it really is delayed fluorescence. This is a bunch of kinetic stuff. I'm not going to ask you guys to solve the kinetics. It's very straightforward. The one thing I would say is everything, all of those K's can be measured independently, except for K fission and K fusion, right? So it's not like we have some unconstrained fit to our kinetics. We only have two that are unconstrained that we need to determine, and those can be determined unambiguously from the shape of a fluorescence decay. Basically, K fission determines when you sort of increase the decay rate, and then where this break is, basically the yield of the triplets, and then K fusion is the lifetime of the delayed fluorescence. That's the dominant channel that you lose triplets from, is that fusion. It turns out that the triplet relaxation rate is about a millisecond in solution. So we're pretty safe in terms of analyzing the kinetics. We can analyze the heck out of the kinetics because we're physical chemists, so that's what we do. So we do Arrhenius plots, right? We measure the rates as a function of temperature, forward, reverse rates. We find that the reverse rate, the fusion rate, is not activated. This is comparable to what people saw in crystals. The forward rate does seem to be activated. You can apply, the activation energy is actually smaller in the biphenyl linked than in the phenyl linked one. But the real question is, are these things any good? Right? Do we get a significant fission yield? Do we generate a lot of triplet pairs for that singlet? And the answer is no. And the reason the answer is no is because the fission rate, right, the rate of splitting into two triplets is very small, on the order of 10 to the 6 inverse seconds, I guess, 10 to the 6 hertz, right? So a microsecond. It takes them roughly a microsecond to split apart. But tetracene's decaying in 20 nanoseconds. That's the singlet lifetime, right? So you barely get any triplet pairs out before the singlet states decay away. So our yields are low, a couple percent. Right? It has to be at least 50% for this to be interesting, right? 50% you'd one photon in, and then half of them generate two extra. Well, it depends on what the others do, but 50% would be an interesting number for triplet yield. So this is the number of singlets that create two triplets. So we did all this. This is relatively old work, but I wanted to get through it to sort of motivate the newer work. I'll skip over I'm going to skip the thing. And say, we know this was first observed in Tetracene, and if you take the kinetics that people did with the crystal seriously, we're way off of what they had in the crystal. Okay, in the crystal, the fission rates are roughly 5 times 10 to the 9. Here we're 3 times 10 to the 6. 1,000 times faster in the crystal. Okay, that's bigger than any energy level change is going to get you. And in principle, if you believe those numbers, the yield's 96%, or if you want to look at triplet yield, it's up around 195%. If you take those kinetics seriously. And so we said, we thought it would be better to stitch two tetracenes together with the covalent bonds between them, because that should help triplet transfer and through bond interactions and things like that. But it turned out that was wrong. So we had to start thinking, what's different between our covalent molecules, which are basically monomeric tetracene, and the crystal, which is not monomeric tetracene. The difference between the crystal and the molecules is that the tetracenes in the crystal are all ordered, they're all lined up next to each other, they're all packed in together, they communicate electronically. Right? They don't exchange electrons, but the Coulomb interaction is enough to delocalize the electronic states inside these aggregates. Okay? So the singlet state is just as I drew it. A singlet state localized on a single tetracene for our covalent dimers. But the singlet state here is a totally different animal. It's delocalized over multiple tetracenes. And to describe that, we think that might be the source of the difference in rates, the factor of 1,000 in rates. So I'm going to digress a bit to talk about how you describe quantitatively these delocalized singlet states. You use this Hamiltonian. We collaborate with Frank Spano a lot. He's the expert at solving this Hamiltonian, although it's been around for 50 years with different people solving it. But the point is you have two predictions. So how do I know that I have this delocalized state, right? I can wave my hands and say, well, states are delocalized in the solids, right? Nobody's going to argue with that. But what I really am curious about is how delocalized is it? Is it big? Is it small? And the way you tell that is by spectroscopy, doing careful spectroscopic measurements, or maybe not so careful, not super high tech. Absorption is okay, but fluorescence is our favorite. All right, so what do you have? If you have a delocalized state, the same thing as saying it's delocalized. It's saying you have many interacting molecules, you have a band. Okay, so coherent transfer, that just means you have a band structure. If you have infinitely many molecules, you have a continuous band. That's not what you have in organic systems, okay? Organic systems are not like inorganic systems where you have a true continuous band and it's worth talking about density states. Here, we just talk about the individual states that come from combining these, from mixing the S1 states of the constituent tetracenes. Oh, about 10 minutes? Oh, okay, fine. Signal already. I'm trying to go at a strong pace. So what happens when you have these states? Well, they're spaced, they're spaced within a few wave numbers, or tens of wave numbers, or hundreds of wave numbers of each other. So this is a case where electronic states have a Boltzmann distribution, right? You're not used to thinking of Boltzmann populations of electronic states, but in these coupled systems, you do have that. And when you lower the temperature, you lower the Boltzmann population, you condense it into the lowest exciton state, if you go to 4K. And that means that, at room temperature, you get a fluorescence spectrum that's a mixture of all the fluorescence spectra of all these electronic states in the band. As you cool it down, some of those electronic states are going to go away. And what you'll see is a different shape of the fluorescence spectrum, right? It's not just that you cool it and everything gets sharper, right? That's typically what you see in spectroscopy, right? You cool everything down to get sharper lines and resolve features. But here it's not just that things get sharper, it's that the shape actually changes. And in this case, the 0-0 peak, this is a vibronic progression or an exciton-phonon progression. You think of these little bumps as phonon sidebands, I guess, if you're a solid-state physicist in the audience. The 0-0 or the zero phonon band becomes hugely pronounced in these molecules, or these aggregates, because you're condensing into a state that has very, very weak phonon or vibrational coupling. This is not technically a phonon, it's an intramolecular vibration. But for the purposes of the Hamiltonians, which is all that we really care about, actually, when you talk about spectroscopy, it's a phonon, it's whatever you want to call it. The second thing is, as you condense into that state, your radiative strength is going to go up, right? Again, these guys not only have different vibronic line shapes, they also have different transition dipole moments. And so you're going to get a mixture of transition dipole moments up here, but down here you're going to get the strongest, it turns out, because of the geometry of the packing. This is what's called a J-type aggregate. Because of that geometry, it turns out that most of the oscillator strength, most of the transition dipole moment is sitting in that lowest K=0 state. That's called superradiance, okay? So superradiance is where you get this big enhancement in your oscillator strength because all the molecules are working together. They're working together to ignore the vibrations. That's why your 0-0 peak goes up. And they're working together to concentrate all the oscillator strength into that transition, that low energy transition. So those are the predictions that you would get from this type of theory. And those are the experimental results that you get, okay? And the nice thing is that once you have a theory that quantitatively describes the vibronic line shape, you can measure the vibronic line shape quantitatively. So here's experiment and here's theory at different temperatures, and you can see that 0-0 peak shoots right up. The nice thing about this data is it's not normalized, right? This is absolute comparison. We're not scaling everything to say the 0-1 peak to make it all look the same, okay? So 0-0 shoots up here, 0-0 shoots up here, down here. So this is one measurement, the line shape. The second measurement is the oscillator strength. As you lower the temperature, it shoots up. You start at about twice the oscillator strength of a monomeric tetracene. As you lower the temperature, it goes up. The best fit is roughly a 3x3 aggregate for both cases. Okay, so we can do two independent spectroscopic measurements, and we can sort of figure out what is this state, how big is this state that we're looking at inside the tetracene crystals, or in this case, a polycrystalline film. Okay, so we're not, in other words, I'm not just making it up that these states are here. Okay, we can quantitatively measure them and characterize everything, right? Their size, their oscillator strength, all those types of things. So that's a nice thing. Now, we go back to Exciton Fission. So, in my group, we're very slow. And while we were being very slow, the field ran by us, in some sense. Pentacene became really a big favorite, and a lot of people started doing spectroscopy on pentacene and tetracene. And what you saw is now there's a controversy, maybe that may be too strong a word in the literature, where Stefan Lockrunner did some very nice experiments where he looked at the transient absorption of pentacene, where we would have expected to see tons of triplets formed through fission. He saw no triplets. And so he said Exciton fission is a myth. That may be too strong. And then there's a theoretical paper that I understand it, but I don't, anyway. Where they say that's right. It's not Exciton fission, it's these bound triplet pairs, but it's really actually a state that's this sort of 2AG state, I think, that was first identified in the polyamines. So it's not, so Exciton fission, again, doesn't work in pentacene. In the meantime, the Los Alamos group published a paper that said, yeah, Exciton fission in pentacene and tetracene, but maybe it depends on whether it's a single crystal or a polycrystalline film. That would be very surprising because exciton fission should be sort of a fundamental property of the crystal structure, not depending on whether it's a, you shouldn't care whether it's a big crystal or a little crystal, I don't think. And also, Mark Baldo made devices based on pentacene, where he said, I get 150% quantum yield based on, and that must be due to exciton fission. So the device guys are saying, great, exciton fission is working great. The photophysical guys are saying there is no exciton fission. And we got worried because pentacene and tetracene are basically the same molecule, right? And we've been taking it for granted all this time that we had a ton of exciton fission in crystalline tetracene, but maybe not. So now, this happens in science all the time. So let me just talk briefly about some of the complications of doing spectroscopy on these solid-state materials. And there are optical problems. So it turns out that if you grow a film of tetracene, and this is also true in pentacene, but again, you don't see much of it in the literature, you see this weird effect where the absorption shape changes. And this is due to a combination, I definitely don't have time to go into this, but it's an interesting thing. It's because you have this, what's called the Davidoff splitting. You have these two Davidoff components here, the first absorption peak. Those are not due to vibrations. Those are due to basically two exciton, it's not really K states, but two polarizations of the exciton, and you can see them, the shape changes, they get sharper, the relative weight changes. And if you're not careful, you'd say, oh, I have some electronic states that depend on thickness. But you don't. It's just an optical effect. Okay? And it's an optical effect that was actually understood in these polycrystalline films by Hofberger and co-workers about 30 years ago in Germany. Another one is, if you make your film thicker, your fluorescence line shape changes, right? You go from this nice thing that I was showing before, if you make it too thick, all of a sudden it shifts red, and then the relative weights of the 0, 0, and 0, 1 peaks change. And so that's, again, you might think, oh, that means it's becoming less delocalized, but that's not true. It's just an optical effect, self-absorption. Okay? So there's a lot of optical artifacts that you can get in solid-state spectroscopy. The best way to avoid those is to make very, very, very thin samples. But the problem with very, very, very thin samples is you get very, very, very low signals. But with fluorescence, that's not a problem, right? Because you're always rolling in signal with fluorescence. So we'll start out with fluorescence. This is just monomeric tetracene in solution. We're going to do a lot of comparisons between the solid and the monomer because that's the best way that I, as a chemist, can sort of keep sane. When you put it in a thin film, you see the textbook delayed fluorescence up, fast decay, and then you see this long component out here. Okay, so again, we seem to have this signature of exciton fission, or at least triplets recombining, right? Beautiful single exponential for the monomer in toluene. There's no funny business going on in tetracene by itself. One thing we did notice is if you do a single crystal and compare it to the thin film, that delayed fluorescence lifetime is much shorter in the thin film. It's not 100 microseconds, it's about 100 nanoseconds. Okay, so morphology does affect the triplet lifetime strongly. And that's easy to understand, right? The triplets are living a long time, they diffuse around, and if you made a crappy film, they're going to find out all the crappy parts and deactivate there. Okay, so but that takes again hundreds of nanoseconds, or at least 100 nanoseconds, even in really poor films that I and my group make. So single crystals again, 50 microseconds is no problem. So we stay with the fluorescence and we say, well, in the old days, everybody measured fluorescence of tetracene crystals. Do our results on polycrystalline film agree with all those old single crystal measurements? Okay, we'd like to check that. And the answer is yes. We can do a pretty good semi-quantitative, again, this is a log plot, right? So it's sort of cheating because things look a lot better on a log plot. But we can take all the old kinetic parameters that people measured back in the 70s and 80s, and we can fit our data using, within a factor of 2 or less, all those kinetic parameters. Okay? So it's not like we're way off here in terms of what people used to study in the original papers where they found exciton fission in tetracene crystals. The one difference, again, is the triplet lifetime. Our triplet lifetime in these polycrystalline films is much shorter than what they quoted for those crystals. Although even in the crystals, they had a spread of roughly 10 to the 2 microseconds to maybe 100 microseconds in terms of triplet lifetimes. So no surprises on the fluorescence of the solid. Okay, so that's reassuring to us. Now we're going to turn to pump probe. But before we do pump probe on the solid, let's do pump probe on the monomer. Because I think I understand pump probe spectroscopy on single molecules. I don't feel that I have a great grip on pump probe spectroscopy of solids because there's a lot of new species in the solids that I have to figure out. But it turns out that the pump probe on monomeric tetracene is also really difficult. And I just want to highlight a couple things. The first is, pump probe, you think, well, I've got bleach and I've got stimulated emission, but then I can also have excited state absorption from those excited states. Okay? And it's all going to be some combination, right? Much harder to analyze than fluorescence, but much more informative also than fluorescence in principle. But here, everything's positive. Everything's an induced absorption in Tetracene. And you can see the stimulated emission in the bleach signals way over here, but they're swamped by induced absorptions. And we can sort of tentatively identify these induced absorptions. The excited states of Tetracene are pretty well known. One thing I would point out is, so first of all, the bleach is there, but it's tiny. It's swamped by the induced absorption from the singlet state. So that means things are going to be complicated. The other thing I would say, a lot of people in solid state spectroscopy identify features in the near IR and say this is a charge transfer exciton, or this is the triplet, or this is something else. But it should be said that that feature is there when you excite the monomer to the singlet state. Right? So you have to be a little careful about assigning near-infrared transitions. Just because they're there in the solid doesn't mean that they're not also there in the single molecule in the liquid. And that's what we see in Tetracene. This has also sort of been seen in anthracene, although these spectroscopies haven't been very well done. So we said, okay, it looks like a mess. What happens if we wait? Tetracene does go to the triplet state. It intersystem crosses with reasonable efficiency, 60%. We should have no more singlet state. Okay, so things should get much cleaner, and they do. And what's more, at long delays, after 20 nanoseconds, it's all in the triplet state. We see a big fat absorption here with a dip in the middle. That dip is the bleach, but it's dominated by this big absorption. That absorption is T1 to Tn excited triplet absorption. Okay, so we do see that in the molecules in the monomer, just as we expect to. And what's more, we can subtract off the bleach. We get a peak at 465. We can calculate an epsilon of around 35,000 inverse moles. All of that is in total agreement with the flash photolysis work. Again, we go back to the flash, we don't want to throw out what everybody's already done and assume that that work is no good. And our work agrees with their work, right? They've looked, this nanosecond flash photolysis, this has been very well characterized, and everything we get agrees with that. So what do we expect for the solid? Well, if it's exciton fission, we know what we expect, right? That singlet is going to appear, and then within, say, 100 picoseconds or so, that's the nominal exciton fission time. Within 100 picoseconds, it's all going to go away, and we're going to be left with one huge whopping triplet absorption. Okay, and that triplet absorption is probably going to be about 465 or maybe a little bit. That's what we expect to see if we're right about exciton fission. Okay, that's what Stefan Lochbruner expected to see. But you don't see that. We see exactly what Stefan saw in the Pentacene, which is a big bleach. It rapidly decays. There's some funny business going on out here, but all of a sudden we get a big negative signal. All of those excited state absorptions that were so pronounced in the singlet don't appear here, and we're left wondering what's going on. But the one thing we know that's not going on is we don't see a big triplet absorption growing up here. So maybe our whole idea about exciton fission was completely wrong. And that would be very disturbing, okay? Because there's a lot of measurements totally independent of optical measurements, ESR, stuff like that, in Tetracene, that is all consistent with exciton fission. Okay, so we're not ready to throw away 30 years of accumulated research. I mean, some of it you could say maybe those guys were losers, okay? But then there's a lot of guys who are really good. And, so what are we going to do? So 2 nanoseconds, you see a little bit of the bleach left, and you see some lumps over here. There's some absorption there, but it's not that big. Certainly not 3 or 4 or 5 times like it was in the solution. So now we have some explaining to do. And the first thing we have to explain is, well, why do we have this huge bleach? Why do we have that huge stimulated absorption? In fact, the main question I had was, why do we have signal at all? Because we're doing these experiments on films with a peak OD of 0.1 or less. And so when my students came through and said, okay, I think I'll hit it. So my students said, oh yeah, this experiment is way more easy than doing it on the solution Tetracene, and I was surprised. But then the reason I was surprised is because I didn't believe the papers that I published, right, which is always a problem. The papers I published said that you have super radiance, right? You have this enhanced oscillator strength, and if you believe that, pump probe becomes a lot easier, because pump probe's a nonlinear measurement. If you have a linear measurement like absorption, you're not sensitive to the coherence length of the exciton. The coherence length is basically how many molecules are ganging up and creating a new excited state that's going to have a bigger transition dipole moment and that isn't going to couple with the vibrations. Okay, that's the coherence length says. If the coherence length is 1, it's just a monomer, right? So Tetracene by itself in solution has n coherence equal to 1. And it turns out that if you do the absorption, it doesn't depend on n coherence. It turns out it cancels out, right? You have a lower density because they're all ganging up, but then you have a higher epsilon because they're all ganging up, and the n cohere and the n cohere cancel out. But if you have delta A, you're doing a pump probe measurement, you can do that math, and you find out that n coherent does not cancel out. So that response, and that's true for any nonlinear measurement, that includes fluorescence, technically. Any nonlinear measurement is going to be, the amplitude of that measurement is going to be sensitive to the coherence length, and then roughly as the order of the nonlinear measurement. So we see a larger delta A signal in the solids, and that's because we have basically larger effective epsilons in the solids. And you can do a ratio of the epsilon that you get from the solid, from the monomer, that you can sort of extract by knowing your fluence and everything. So we know the fluences, and we know the linear absorption of the samples. We measure the delta A, so you can do that ratio. And you find out that the effective epsilon of the solid is 6 times, roughly, let's take 6 plus minus 1 at least, that of the monomer. Okay, so we do have a super radiant enhancement. That's why we have this monster S0 S1 absorption. That's why we have a big negative signal. You don't have that enhancement of the S0 S1 transition in the monomer. This is also larger than what we got from our old fluorescence measurements back in 2004. So that's a little disturbing too. Why is 6 bigger? But again, that's not the only thing we can measure. We can also try to extract the line shape of this fast decaying component, the stimulated emission that we see going away so quickly. I'm going to call it stimulated emission and justify it in the following way. You can try to pull out a vibronic spectrum of that, and what you see is it's almost all the 0,0 peak. There's very little 0,1, and to be honest, just the way this data is plotted, it probably overestimates the 0,1. But at least a factor of 2 less of the 0,1 peak. Again, that's our other weapon to estimate coherence length. So whatever we're seeing in the first 10 picoseconds, it's big, it's fast decaying, and it's more delocalized than what we were pulling out of our picosecond fluorescence measurements back in 2004. And why is that? Well, what we've learned, just parenthetically, is anytime you deal with an aggregated system, organics are different than inorganics, right? Inorganics, people can meaningfully talk about defects, densities, part per billion, part per trillion, stuff like that. Okay, that's meaningless for organics, and the reason for that is that the energies are so similar. For the good crystal and the bad crystal, the defect, there's almost no difference in energies. The reason for that is you don't have covalent bonds locking the atoms into place, right? That you just have to rely on van der Waals forces for the distance. So what we think actually is that the fluorescence that you mostly detect from Tetracene is probably due to what's called a linear slip dislocation defect, and we have better evidence for that in anthracene, which we published. And that this guy is some other, it may be a defect or it's something else. It's a new short-lived species that decays in a 10 picosecond time scale. So as you go farther in time, you see different states. That's the case. So that's why the singlet is so big. But why is the triplet so small? Well, one answer is it's not there. Okay, but we don't like that answer, so we're going to try another answer. The answer is that it has to do, again, with the polycrystalline nature of these films. Okay, Tetracene and Pentacene, and Stefan knew this, align on the surface almost perpendicular. They're just tilted at a slight angle from the surface. This is the way these crystallites grow on flat surfaces. Now the S0 to S1 transition, the one that gives rise to superradiance, the one that creates these exciton states that I keep talking about, is exactly perpendicular to the molecule's long axis, right? It's counterintuitive, I guess. The triplet to triplet transition is parallel to the long axis. So when the light comes in, right, it's the dipole selection, it's mu dot E. Well, E is going to be somehow parallel to the substrate because I have to shoot my light at the substrate, right? So the parent polarization is going like this. And when I try to dot my mu vector into that, I'm not going to have very good success with the triplet. But it's going to go great for the singlet, right? That's going to have a very nice, strong interaction. And this was mentioned, but not quantitatively described in an earlier paper. We sort of quantitated it, and it's a big, big effect. And a factor of 20 even without the superradiant enhancements with normal incidence, right? So just from the orientation of the crystallites, right? They're not randomly oriented. If they were, this would be an easier experiment, but they're typically not randomly oriented on the substrate. The triplet has the bad orientation to interact with the light's polarization, and it appears up to 20 times smaller than the singlet. And this is not even taking into account the fact that the singlet's bigger because it's got this superradiant enhancement. Okay, so once you're talking about a factor of 20, you can miss that in the signal-to-noise of your transient absorption experiments. All right, and coming in at an angle does not help very much, although it does help, and we didn't do that experiment. It was done in Pentacene, and to be honest, the amplitude of the triplet that they see in Pentacene is exactly what our calculations say it should be if we have 100% triplet. But this is not very satisfying, right? I'm arguing, is it evidence of absence is not absence of evidence? Something like that? Or it's vice versa. My Dick Cheney quotes are eluding me. This is an excuse for why we don't see the triplets. But you could say, well, you don't see the triplets, but it still could be that the triplets aren't there. So, then you get, you tell your grad student to build a 100 nanosecond delay line, and then because he's a new grad student, he does it. And you say, okay, we have a delayed fluorescence decay. We're pretty sure that that delayed fluorescence is coming from triplets. If that's all there is, we should be able to measure the bleach. And the bleach is going to fill in. If triplets are a minority species, the bleach is going to fill in, but maybe it'll be a lot slower, right? Because there's something else there, some dark state like a charge transfer state as was postulated for pentacene. But if you go and measure the bleach and watch it fill in, that rate of recovery of the bleach, right, we can get about a factor, about a decade, a little more than a decade, exactly mirrors the rate of decay of the delayed fluorescence, which we know is the triplets. Okay? So if we make the assumption, which I think is very safe, that the delayed fluorescence is due to triplets, and then we say, well, is there anything else? Well, if there is, the bleach should be different, but it's not different. It's the same recovery time as the decay of the delayed fluorescence. And if you have a different sample or a different intensity and you change this decay rate, this decay rate changes as well by the same way. So it doesn't look like there's something else. Right? It doesn't look like there's some mysterious bound triplet pair or charge transfer state in Tetracene. It looks like everything can be explained with triplets. You just have to modify the old traditional picture a little bit. Here's our modification. One is you have to take seriously your own results, I guess, that these delocalized states exist and that they can have a big effect on the transient absorption spectroscopy. Also, then you have defect states. They don't have a big effect on the transient absorption spectroscopy, but they have a big effect on the luminescence, right? Luminescence is always going to be very sensitive to defects. So in some cases, what we see, we believe, is this initial state decays very rapidly. That's our 10 picoseconds. Some of it goes to a defect state that then decays over 100 picoseconds. That's what you see in the luminescence. So this guy is a good shadow for the sort of heavy lifting singlet state, but he's not the main story. The main story is this, and the main story is these guys. These guys recover. You get defect, you get that delayed fluorescence, and they recover, and the bleach recovers, and everything seems to be sort of self-consistent. None of this is too surprising for people who know about spectroscopy of aggregates, right? You believe that these states exist. They've been seen many times in many different types of aggregates, including light harvesting complex. And anyone who knows about molecular crystals knows that they're full of defects for thermodynamic reasons, not just because we're lousy chemists. So with that, now we feel a lot better. I'm going to sum up here with some conclusions. One conclusion is that you can build and design these molecules, these covalent molecules. They do exhibit fission. We've seen it. It's been surmised in phenylisobenzylfuran dimers as well. I wouldn't say it's super conclusive evidence. But low yields, right? Not interesting from a practical standpoint. Now the news here is no news, right? You don't get a lot of points for saying that everybody was right all along, just adding a few things. But I do think that they were right all along, and I think people are maybe getting a little worked up about saying that there's no exciton fission where everybody said there was exciton fission. I mean, we think we can explain all those results in a self-consistent way. The last question, which is what I started the talk with, but which I have not answered, right? So, but I'm going to hazard some guess, is what is the role of this delocalized states in enhancing exciton fission? Are they necessary or not? Now, there's a recent theoretical paper by Grayson and Ratner that says they're not. They say that electronic coupling, this electronic coupling that creates the delocalized states, doesn't really play a role in exciton fission. And I'm starting to believe that they're right. But let me say something that might explain both of these. Okay, you postulate the mechanism of exciton fission. It involves charge transfer states. How do you get a low-line charge transfer state to mix in and interact with those singlet states? It's present in the crystal, that's for sure. In fact, the crystal, these are unpublished calculations from Bardeen and Spano and the whole whatever army they have working at Georgia Tech right now. But the army says that that the reason you have strong coupling in Tetracene is because these low-line charge transfer states mix in and build up your Davidoff coupling. So in other words, low-line charge transfer states make big coupling between molecules. But low-line charge transfer states are also what you want to have that fission mechanism be operative, right? Because it involves an intermediate charge transfer state. So it may be that this does not make fission possible. It may be that this is a symptom of a condition, namely a low-line charge transfer exciton state that enhances both processes. It increases your electronic coupling and it increases your fission rate. And if that's true, it's bad news for molecules like this, because it's not clear how you create a charge transfer state. You know, here it's easy because you have this huge polarizable medium that can lower all those energies. Here it's not so easy to see how you would get a charge transfer state to be close in energy easily. I'm going to stop. I'm going to just end up with a conclusion. You're going to see, here I've sort of said it, but I haven't said it very definitely, but you're going to see, I think I can safely predict, that you will see a bunch of papers, 200% yields for triplet excitons, published if they're not already published, in the very near future. Okay, so to get a 200% yield of triplet excitons is not going to be some huge task. I think it's been done in some materials, and it's going to be done in a lot of other materials. And so the question is, once you've got it, can you do anything with it? There's some details on characterization. I've talked about that in the talk, so I'm going to skip over that. One thing is, all of these are going to be in aggregates. So can you synthesize a molecule? You know, you'd like to have it all self-contained in one molecule. You could mix in with PCBM or something like that. Okay? But it's not clear how you would make a molecule that has high exciton fission efficiency to do that. In aggregates, I think it's going to be pretty common. But you know, you have a lot of trouble mixing aggregates with blending them with P3HT and stuff like that. Maybe P3HT really does have high exciton fission efficiency. I mean, that would be lucky, I suppose, if it did. So there's a synthetic challenge. The other challenge related to that is a theoretical challenge. We really need a better understanding of how this occurs, because that'll help guide the synthetic efforts and tell whether it's even possible in an isolated molecule to have efficient exciton fission. Practical issues, again, I think that's actually not such a huge issue. People say, well, even if you can generate the triplets, how do you ionize them, right? That's the biggest criticism I hear. So what if you generate a lot of triplets? You can't ionize them, you can't make charge carriers out of them, so on. But the reality is, this is probably, it's not just Mark Baldo, right? There are a lot of people building devices out of these materials, and I would point you to the work of Warman, who sort of has solar cells based on triplets, very convincing evidence, using time-resolved microwaves. And then Carl Leo also has a recent paper where he looks at Pentacene and says, we think the triplets are the main actors there. All right, so it's 2%, right? It's not very high yield, but these are bilayer heterojunctions, right? They haven't even tried to do the bulk heterojunction trick there. So maybe if you can figure out a way to make a bulk heterojunction out of Pentacene, you might be able to get the high efficiencies and the advantages of exciton fission in that type of material. So, the bigger question is, will that screw up things like charge transport, which you also need to have a functioning device, right? It's easy to get exciton fission to occur, but then incorporating it all in a functioning device with high efficiency, as everybody in this room knows, is extremely challenging. It can be extremely challenging, and it never seems to work the way you want. But anyway, I think I'm done, hopefully on time, more or less.
One thing that the molecule shows do is basically stack with the aromatic rings. I mean, I know from some of the reading that in flexible hexagons, there's significant low-line charge transfer state.
That's right, that's right. So the thing here with exciton fission, it's a little bit of a subtle point. You want to have a triplet pair state that's kind of the lowest excited state. Now, if you pi stack, everybody knows that you can get a charge transfer state that's pretty low in energy too. So you want the charge transfer state to be above the triplet pair state. Once it goes below, everything's just going to go to the charge transfer state, and you won't get your two triplet excitons. So it's kind of a balancing act. So if you pi stack, usually that charge transfer exciton is below the triplet pair state. You can build tetracenes that pi stack, and they show excimer fluorescence and everything, and you don't get much in the way of nobody's really measured it carefully, but that's probably bad for exciton fission, because now so you have to tune the charge transfer. That's the thinking right now, is you want to be able to tune it, not below, but a little above, but not too far above. So the crystal engineering you might want to think about.
Did you think about to make the several intermediate points between a single crystal and polycrystalline film, like to make microcrystalline film or nanocrystalline whatever? Because when you have a film, especially thin film, you have an interface. That means you're having trouble. For example, in Tetracene, it has been recognized pretty more packing motifs on interface. So maybe this is the same case.
Yeah. So what we found is you can grow polycrystalline films of different thicknesses, right? So I guess the question is the interface with what? It's an interface with a vacuum or other tetracenes. Doesn't seem to have much effect on this triplet lifetime. In other words, that triplet lifetime thing doesn't seem to be necessarily quenching in an interface. Actually, we would love for that to be the case, because then we could replace the interface with TiO2 or something and we'd be in business. But that doesn't seem to be the case. It seems to be maybe defect density or something like that. I mean, we're not averse to saying that it's a problem with diffusion to the interface that quenches those triplets. But we haven't seen, and as for growing, say, a good crystal of the same quality of different sizes, that's not very easy to do, actually. So it turns out that the methods that you use are typically different. We've tried this vapor diffusion method where we grow, typically we just get big crystals and little crystals. And the method doesn't seem to matter that much in terms of the triplet lifetime. So, it could be the interface, but it could also be just defect density within the crystal that is killing the triplets. And we don't have a good way to sort of continuously vary the crystal size and be sure that the crystals have the same, say, defect density. That's what you really need to do. Is, not just that they're different size crystals, but they're also the same quality crystals, same purity, stuff like that.
By the way, do you grow the films from the vacuum or from the inert gauges?
I'm sorry, the spectroscopy or the?
No.
Growing. Yeah, we do both. So we do both sort of high vacuum, vapor deposition. That's good for growing very thin films. It's harder to get control with sort of the vapor growth. The nice thing about the vapor growth is it will give you a distribution of crystal sizes. For the thin films, it doesn't matter which method you use. It turns out inert gas, argon, we haven't used H2, but the inert flowing gas versus fast vacuum thermal deposition, and actually other methods as well, reprecipitation into water. It's surprisingly robust, the results that we get with preparation. The only thing that seems to tune maybe is that triplet lifetime, but even then not very much if you have nano-sized crystals. But we tried many different ways.
One last question.
How about introducing intentional defects? You have a crystal and put it in X-ray or electron beam, and always measuring the same crystal with different densities of defects that you introduce.
Yeah, no, that would be a good experiment, I think, because right now our defects are unintentional defects, right? We don't have a good way to vary their density. We also don't really know what the starting density is. So if you start putting in defects, the question is, if you have 1 million defects and you put in 10, then you wouldn't see any effect. But people have done those. You can. The good way to do that is strain. Okay, with single crystals, that's the nice way to controllably introduce or accentuate defects is by putting strain on a single crystal. So what we would really love to do is grow a single crystal that's 30 nanometers thick that we can put strain on and do things like that. But technically that's quite difficult to do. And so we end up with these polycrystalline films, but you can't do the strain tricks and things that people have done as sort of traditional things. But yeah, we sort of thought about that, dopants maybe. X-rays would sort of be on our capability right now. But that would be a good, that's definitely a good idea, one we'd like to explore more.
Okay, let's thank Chris one final time.